Chapter 10, Lesson 3. In this lesson we'll talk about the famous ideal gas law. Now this law essentially combines the three previous laws that we've looked at: Boyle's law, Charles' law, and Avogadro's law. We call that Boyle's law determines or explains that volume and pressure are inversely related, and here we can represent that using this symbol that just means in general inversely or just means related to one another. This is kind of like the equal sign, but the qualitative version of the equal sign. In order to have an equal sign, we have to have a constant in there. And then we said that Charles' law dealt with volume and temperature. Those were directly related. And then volume and moles were dealt with Avogadro's law, also directly related. What we could do, essentially, is combine these three into one. And here's what we get. We say that volume is directly related or proportional to moles, temperature, and pressure, which essentially means if you increase any of these here, volume will also increase. If you add an amount of gas to your vessel, the volume of the vessel will increase. If you increase the temperature, the volume will increase, and so on and so forth. And if you increase pressure, then, because we're dividing by pressure, that will cause volume to decrease, because dividing by a bigger number gives you a smaller value, is the idea. So before we tie all three of these laws together, when we tie them together, we'll define what's called the gas constant, R, which is an extremely important constant, and we'll use this constant in many calculations following. Now, the gas constant can have different values based on the subunits that you use. So if you decide to use, for example, liters and atmospheres, moles, and Kelvin, here will be your R value. Now this is the most common R value that we will use. So if you want to put most common here, most of our equations essentially deal with this or make the use of this gas constant. But you can also define it in many other ways. Another famous one is using this one. We'll see, we'll have to use this one later on eventually in the semester. But any of these essentially can be used depending on the subunits that you are employing. So we will then be able to transform this in general a symbol of proportionality into a true equal sign. And remember, an equal sign, then it creates an equation, and that equation has to have a constant, and then our constant is R, is the idea. Now this actually becomes famously PV equals nRT. This is the famous gas law equation, which we will use from now on in many calculations, and we encourage you to somehow make an effort to allow this equation to show up in your life as a representation of the importance of chemistry in your life. Maybe get yourself a license plate that says PV equals nRT. It's possible that PV equals nRT is already taken, so you can do PV nRT 1 or 2 or 3. Some of those may be available. So in order to show you the use of this equation, why don't we do this problem? Now this problem is going to be a bit involved, so make sure you got enough room to write down, and as you'll see, these problems will be a bit big because of the many factors that we have to consider here. So calcium carbonate, a famous solid, decomposes into calcium oxide and then CO2 gas, the fun-loving carbon dioxide. A sample of this solid is decomposed, and the gas is collected in a 250 milliliter flask. After the decomposition is complete, the gas has a pressure of 1.3 atmospheres and a temperature of 31 degrees Celsius. How many moles of CO2 gas were generated? And then another question, what would be the pressure if all the gas was moved to a 500 ml flask at 0 degrees Celsius? The second part essentially is a combined gas law equation. But the first part will be an ideal, this PV nRT gas law equation. So let's go ahead and put down our equation. PV equals nRT. It looks like the question is asking us to solve for moles. And so what we'll have to do is rearrange firstly the equation to solve for moles. In this case, we'll rearrange by dividing the R and the T on the other side. So we'll have moles equals PV divided by RT. Hopefully this operation is trivial. And then let's go ahead and list the parameters that we are given in the problem. First of all, we're given a volume of 250 milliliters. Three significant figures there, although that decimal place I see is not there, so technically we got 2 sig figs. We'll have to go with that, just 2 sig figs. 250 milliliters. It looks like our pressure is given to us as 1.3 atmospheres. Looks like our temperature is given to us as 31 degrees Celsius. The R constant is well known, and I think we're justified in just saying 0.0821. Just 3 significant figures will usually do the job. Now the units of this gas constant R are the following. Liters times atmospheres divided by mole Kelvin. So if you look back at the units, you'll see that these units are actually that first R value that we took a look at. And now, essentially, it's a matter of plugging the values into the equation. The only thing we have to make sure that each one of these values corresponds to the units of our selected value of the gas constant. So, our volume must be in liters, our pressure in atmospheres, our temperature in Kelvin. And so it looks like we'll have to convert our volume to liters. Now, 250 milliliters converted to liters is simply divided by 1,000, and so we should get down to 0.250 liters. If you have trouble doing this, consult some dimensional analysis problems. And then our atmosphere looks like is good. We're matching there. Our temperature must be in Kelvin, as is always the case when we're doing problems using temperature. So let's go ahead and add 273. And this gives us 304 Kelvin. Now we're ready to plug and chug. So our moles is equal to pressure 1.3 atm multiplied by a volume which is 0.250 liters divided by our gas constant, 0.0821 liters atmospheres moles Kelvin, multiplied by, on the bottom, our temperature, which is 304. Now, if you plug this into your calculator, and then we'll take a look at how the units cancel out, but go and plug it in, see what you get. 1.3 times 0.250 divided by 0.0821 and 304. So it looks like our value for n came out to be 0.0130. Now, because we're dealing with two significant figures, it looks like 0.013 will suffice moles. So here is how many moles of gas are contained in a 250 milliliter vessel under these conditions. Not many moles, but recall that we talked about how a 1 mole of gas takes up an enormous amount of volume comparatively. So this sounds to be pretty accurate. Now the second part, this was just part A. The second part of the problem, part B, asked us what would happen if, what would the pressure be if all the gas is moved to a different container. Technically, that's twice as big under temperature conditions that are a little bit colder. So why don't we do this on the next page, because we'll need a little bit of room, and it'll be a combined gas law problem. Actually, before we do that, let me show you something that's worthwhile to see with the gas constant R. Now, if you take this PV equals nRT equation, and you rearrange it to solve for the gas constant R, we'll have to divide by NT on both sides. What we'll get is PV divided by NT. And this is precisely, if you take a look, the way the units are set up. You get pressure and volume on top, and you got mole and temperature on the bottom. So this is just in passing why the units of R are such. And then if you take a look, if we follow this rule, then your equation shows how the units cancel out. Atmospheres cancel out with atmospheres, liters cancel out with liters, and then Kelvin cancels out with Kelvin, and what we are left with are moles. And that's essentially what we want to do here in the end. Let's take up this part B of this equation. So part B says we have ourselves some initial and some final conditions, and we're asking what the pressure would be like. So let's take a look at pressures, volumes, and temperatures. Recall this is how we use the ratio method. So we get P1, P2, V1, V2, T1, and T2. If we fill these values in, we'll see that with the first pressure, we got ourselves 1.3 atm. The second pressure is the one we will try to find out. Let's make that a question mark. The first volume in this case is 250 mils. The second is 500 mils. The first temperature is 31 degrees Celsius, which we converted to 304 Kelvin. The second temperature is 0 degrees Celsius, which would be 273 Kelvin. Recall that temperatures must be in the units of Kelvin. And then using the ratio method, our pressure, 1.3 atmospheres, will be changed by both the volume and the temperature. In this case, our volume goes up, increases, so our pressure will have to decrease because volume and pressure are inversely related. This means to make a decrease, we will put the small number on top. We'll put 250 milliliters on top and 500 milliliters on the bottom, because an increase in volume must cause a decrease in pressure. Now, notice that I did not convert to liters here, because the ratio, if I were to convert to liters, the ratio would be 250 over 0.500, which would be exactly the same as I've got up there. The ratio itself, as long as the units are the same, you can actually use different units than the R constant requires. Then if you take a look at the temperature, it looks like our temperature goes down. When temperature goes down, pressure goes down. So to make pressure go down, we'll put the small number on top. This will ensure that temperature pulls pressure down according to the gas law. And then just multiply across the top and divide across the bottom, and you should get yourself, let's see, 1.3 multiplied by 250 divided by 500 multiplied by 273 divided by 304. So we should get ourselves 0.583. 0.58337, and really we're dealing with roughly 2 sig figs. Looks like our 500, actually we're dealing with 1 sig fig because of this 500. So really all we can say is that we have ourselves 0.6 atm for our answer, following significant figure rules. And this will conclude lesson 3 of chapter 10, a short lesson.